Well, good evening and welcome. You are tuned into AP Physics Live or AP Live, and tonight my name is Roger Siegel, and we are going to be reviewing for the AP Physics C Electricity and Magnetism exam. I'm coming to you live from Sarasota, Florida, and as always, I have my friend Kristen Gonzalez Vega in Texas. Hello, Kristen.
Hey, Roger. Welcome, everybody. Happy Friday.
Absolutely. Happy Friday. I'm glad it's Friday. I'll bet you are too. Well, as I said, we're reviewing for the AP Physics C Electricity and Magnetism exam that's going to be on May 11th. And we're happy to help you get ready. We've been, tonight is our 15th night, the end of our third week of review. So we've been reviewing for a long time, and we got one more week of review next week to complete the curriculum. And then the following week, Kristen and I are going to be doing mock problems with you during the week, just as you would do mocks if we were in school. We've got mocks for you, and we're going to give you time to do them, and we're going to go over them with you and get you ready for the exam. All right, let me get into what we're doing tonight and start sharing here, and we'll get moving, get this boat moving. Here we are. So today, as I said, my name is Roger. Tonight we're doing more circuits, current and resistance, section 3.1. And I'm coming to you from Sarasota, Florida, where I teach physics, and Kristen is coming to you from Frisco, Texas. I did mention the time of the exam. I want to point out the date. I did mention it was the 11th. I want to mention the times, and you can see they're right here. Make sure that you have your computer hookup. Make sure that you'll have a quiet place. Talk to whoever you need to, and if you need to make special arrangements, start looking into that now so you can be ready to take this exam and to be successful. And so let's go ahead and move on to see what's next. Here we are. This is, as I said, what we've been doing. This is our third week of review and one before the last. And we are finishing up with conductors and capacitors. And now we're doing circuits, current and resistance, Ohm's law. Okay. So today we're going to look at Ohm's law again, and we're going to talk again about resistivity. And we are going to look at different geometries of material and see how that affects the particular resistance of the different resistors. And we're going to do some problems that have to do with internal resistance. Also, tonight we've got two problems that focus on labs. And Kristen and I don't know what's going to be on the exam. I wish we did. But we do get a sense of what AP is telling us. And so we think these are really good problems to help you get ready. All right, so what did we learn last night? What are we reviewing tonight? And where I want to start is resistance. So remember, resistance is what is blocking current, what impedes the current. The higher resistance you have, the less current will flow, and the less the charges will flow. Remember what resistance is, the symbol R, and I think we talked about this last night. Yeah, of course we did. The units for resistance are ohms, so we'll look at the different resistance ohms. We talked about current last night. Current is the flow of charge through a wire, and current is symbolized by the large letter I. We measure it in amperes, and amperes are coulombs per second. All right, and I really want you to think about that. When you say amperes, you might even say coulombs per second. And when I teach, I'm going to do that because I want to remind myself what is an ampere, what's really happening here. And I want to actually imagine charges moving through the wire. Now remember, they're moving very slowly on the order of millimeters per second, okay, in most wires, but they are moving nonetheless through the wire. And so we talked about resistance. We'll see that again, the size and the shape of the material. We'll look at this formula again tonight, and that is the formula resistance and the resistance of a substance or of an object is equal to its resistivity, rho, times its length times its area. We're also going to use Ohm's law again tonight. And so Ohm's law says that V is equal to IR. And we also very often will look at I is equal to V over R. And so Ohm's law is articulated either way. And we'll talk about what it means when these things change and how our circuits get affected. The other thing we're going to look at again tonight is internal resistance. The idea that the battery that is powering your whatever, your phone or your flashlight, when you hook it up to a voltmeter and you test it, it says 1.5 volts or 1.3 volts, and that matches the voltage that's printed on the side. That's called the EMF. But all batteries, except for the ideal ones that only exist on paper in physics classes, all batteries have internal resistance. And so tonight we're going to look at that concept of internal resistance, how we can measure it, how we can account for it when we do experiments. And so remember, the internal resistance is something that's in the battery. It has to do with the physical and chemical realities of how a battery works, which we don't go into in this class. You probably go into it more in a chemistry class. But the internal resistance is there, and so we're going to do some problems identifying it and mitigating for it. Okay, so as I explained, tonight is a continuation of last night's work. We're not really introducing any new concepts. We're going to continue to develop the concepts we did last night. And so it's kind of early, but I'm going to throw it over to Kristen I was going to say Plano, but she doesn't live in Plano. That's near there. I'm going to throw it over to Kristen in Frisco, Texas, and she's going to do some problems, and then we'll do some experimental ones after that. Take it away, Kristen.
All right, thanks, Roger. So we're going to look at some multiple choice questions here so we can kind of talk about the concepts going on. And the first one is we have two conducting cylindrical wires are made out of the same material. We have wire X and wire Y, and wire X has twice the length and twice the diameter of Y. So we kind of draw these out. We've got Y and we've got X, and X has twice the length and also has twice the diameter. Okay, but they're made of the same material, so they both have the same resistivity. We want to know what the ratio of the resistances is going to be. So we know resistance is resistivity times length over area. So I'm going to write X in terms of Y first. So the resistance of X, we can figure out it has the same resistivity, right? So we could really put in that it's 1 times the resistivity of Y. And the length is twice times the length of Y. And now let's look at the area. If we were to find that cross-sectional area here, which is pi r squared, then really if this has twice the diameter, that means it has twice the radius, and therefore 4 times the area that Y has. So if we were to find that resistivity, the resistance of X is going to be 1 times 2 over 4, which is 1/2. So our X is equal to half the resistance of resistor Y. Okay, so if we want a ratio of our X to our Y, well, I'm going to bring Y over by dividing, and I'm left with the 1/2. Okay, so our X has half the resistance that our Y has. All right, let's look here at these. So you've got 5 different shapes here of resistors. The lengths and the cross-sectional areas are indicated, and they are again made of the same material with the same resistivity. And we want to know which of these 5 conductors would have the greatest resistance. So take a second, tell me what you get. If I want a big resistance, what kind of length do I want? Short length, long length? Well, if I want a big resistance, I want a big number on the top. So we want one that's going to be long, right? So that's going to get rid of A and C and E. And if I want a big resistance, what kind of area do I want? Well, since area is on the bottom, there's that inverse relationship. I want a small area. So D changes. It starts with a big area, then goes small. So if we look at B, that's going to have an even greater resistance than D does. So if we want a big resistance, we want a short, skinny wire. And if we want a small resistance, we would want a short, fat wire. What if we look at this one? We got a 12-volt storage battery with an internal resistance of 2 ohms being charged by a current of 2 amperes as shown in the diagram above. Under these circumstances, a voltmeter connected across the terminals of the battery will read. So if we were to define that potential difference across the battery, well, what we're really essentially looking for is what is that, what we call terminal voltage, right? So if I take my battery out of my remote and I just measure what the potential differences across there, there will be a potential difference, even if it's not in a circuit, right? If it's a 1.5 volt battery, then it would read 1.5 volts brand new, maybe out of the package. But the minute I put that into a circuit and there's a current passing through, then that voltage drop is going to change. And what that reading is across that battery once it's now in the circuit is what we call the terminal voltage. I like to kind of call it the useful voltage, or what you're actually getting out of that battery when it's in the circuit. So we're looking for the terminal voltage. And the way we can find that terminal voltage, it's the EMF of the battery, what we get when it's not connected to the circuit, minus whatever that voltage drop of the internal resistance would be, right? So another way we could write this is we could say, well, we've got our battery and we've got that little resistor R, right? That internal resistance of the battery. So the terminal voltage would be the EMF of the battery minus whatever the voltage drop or potential difference across that internal resistance would be. So I could say that's times IR. And then we can plug in the EMF of the battery is 12 volts. The current is 2 amps times our unknown resistance R. And if we put in that the terminal voltage is what we're looking for. The internal resistance is 2 amps. I'm sorry, guys. I'm thinking ahead. There's another one we're going to do in a second. That's the reverse. So this is what we're looking for, and our resistance is 2 ohms. So if we've got our 2 amps times our 2 ohms, that's going to give us 4. And our 12 volts minus our 4 volts is going to give us 8 volts, which is B. Okay, back to resistance. We got 2 resistors, same length, same material, but connected in series to a battery shown above. Resistor 2 has a greater cross-sectional area than resistor 1. And we want to know which of the following quantities has the same value for each of these resistors. So what's going to be the same for resistor 1 and resistor 2? So read those answer choices and let's see what you get. Hopefully what should stand out there pretty quickly for you is the current. Because these are in what with each other? Series. And we know that if the current is flowing out through the battery, the positive side of that battery, well, as we go around, there's nowhere else for that current to flow. So if we have no junctions or no other branches in our circuit, then the current has to be the same everywhere in there. Well, let's look at some other things on why these other ones are not correct, right? Let's look at D. Why is the current per unit area not correct? Last night, we talked about what that current density is, right? That J is equal to the current per cross-sectional unit area of that. Well, their cross-sectional areas are different, right? But their currents are the same, so they cannot have that same current density. Okay, The resistance, why would the resistance not be the same? Because they have the same length and they have the same resistivity. If their area is different, the resistance has to be different. Right? Okay, what about the electric field strength within the resistor? That one's maybe not as obvious as some of these other answers are and why it's wrong. Another equation that we derived last night was that the electric field within a conductor or wire, whatever it is equal to the current density times the resistivity. Well, here the resistivity is the same, but we just determined that the current density J is not the same. So they can't have that same electric field going through them. Okay, and the potential difference between the two ends. So if I were to put a voltmeter across each of these, why is the potential difference across each resistor different? Well, their resistance is different. So if their resistance is different and we used Ohm's law, if we know they have the same current passing through them, but we know that number one, or I, whatever we want to call this, that resistor, since it has the same length but a skinnier cross-sectional area, it will have a bigger resistance. And so since it has a bigger resistance for the same amount of current, it would actually have a greater potential difference across it than number two does. Okay. What about this one? The EMF of a battery is 12 volts. When the battery delivers a current of 0.5 amperes to a load, the potential difference between the terminals of the battery is 10 volts. The internal resistance of the battery is, so I'm going to draw it out. I want you to think about it here for a second on how you could find that. Okay, so if we have our battery here, and remember the way we indicate whether it has internal resistance or not is we have this little resistor R, and we've got this dotted line drawn around our battery. Okay, so we want to know what is the internal resistance of this battery. So let's look at what we know. We know the current. I know that the EMF of the battery is 12 volts, and I know that the terminal voltage, potential difference across the battery when it's in the circuit, is equal to 10 volts. And so if we want to know what the internal resistance is, well, we go back to what we were saying before. The terminal voltage is equal to the EMF of the battery minus that voltage drop of that internal resistance, which is equal to I times little r. Still using Ohm's law right here. So this is the voltage drop across that little resistor. So we know now the terminal voltage is 10 volts. 12 volts is the EMF of the battery. 0.5 is our current. And we want to know what our internal resistance is. So if I find that difference between these, that gives me 2 volts. And so then if we solve for R, 2 divided by 0.5 gives us 4 ohms, which is C. Okay, let's do one more of these with internal resistance. So we've got our circuit here. We've got our battery, 20 volts is the EMF of that battery. There is an internal resistance. And we have 2 resistors, a 30 ohm resistor and a 60 ohm resistor. And we know the current is 0.8 amperes. So what is that internal resistance? So again, I'm going to give you just a couple of minutes here to think through how you would do this. What are your steps you're going to have to take to get that internal resistance? Where I would start is what I know. I know that the total current being supplied by that battery going through my circuit is 0.8 amps. And I know the EMF of my battery is 20 volts. So I would use Ohm's law, right? We got to find what should the equivalent resistance of my circuit be, right? Let's find what that equivalent resistance is. So if we use Ohm's law, and we solve for R, well, 20 divided by 0.8 is going to give me 25 ohms. So my total resistance of my circuit should be 25 ohms. Well, let's see what these two resistors here in the circuit would give us for an equivalent resistance. So we got to recognize, are these in series or are they in parallel? And if we look at them, right, we've got this junction right here where current could split one way or the other, which means these resistors are in parallel. So how do we combine resistors in parallel? Well, 1 over that equivalent resistance would be 1 over 30 ohms plus 1 over 60 ohms. If I make this 2 for 60, then I get 3 over 60, but that's 1 over R. So again, we got to flip that over and we get that this is 20 ohms. So this portion of the circuit has a total resistance of 20 ohms, but I need to have 5 ohms total for this. Okay, the way we treat that internal resistance is we treat that it's in series with the battery, right? So we treat it like it's almost a separate resistor that's in series with the battery. So if this is in series, we would want to add on to the resistance for it. So we want 20 ohms plus whatever our internal resistance is to equal my 25 ohms, which gives us 5. Okay, so there's some practice with that resistance and with internal resistance of batteries. So let's take a look at a couple of lab-based free response problems and give it back to Roger in Florida.
Sorry. All right. Thank you so much, Kristen. Well, I want to tell you, Kristen, and anyone else who's listening, that we got some good storms coming through Sarasota right now. So if I cut out, you're going to have to take over. All right. All right. Just so you're ready. I just looked at it. It's brutal, but we're safe in here. All right, great. Now, let's go ahead and share. Let me share my screen here, and I'll show you something I've been working on. I think you're going to enjoy. And that is, again, the Phet simulation. And this is a Phet simulation that Kristen had shown you, showed you last night. And I wanted to bring it up again because it is so useful and so great for trying to understand these concepts of electricity. You know, one of the hardest things about teaching E&M is so much of it is not visible. And so we have to have so many proxies and metaphors and stand-ins, and they're important. And it's important to know them. So here, let's take a look at this. So this is my circuit. I've got the different, let me just turn some things off here. I'm going to turn off the labels here. And so let me see if I can turn off. Okay, good. So what I have here in this circuit is I've got a battery over here on the left. I've got 2 resistors over here. I've got a switch and I've got an ammeter. And then over here, I've got a voltmeter. And I have purposefully drawn this battery in a vertical orientation and these resistors in a downward orientation, not because it has anything to do with how they function electrically. You can have this upside down, right side up, it doesn't matter. But how they function conceptually, if we can think of potential as a rise in potential, we use those words, or a drop in potential. If we can think of that and use the gravity as a stand-in to kind of a bridge for us to understand how this works, it's often very helpful. And there's other things that we can do to understand how this works, and that's why the simulation is so useful. So one of the things I can do is I can turn on, I think one of the things I'd like to do first is change over to the symbols that we would draw if we were drawing this out, because it's important to know that this is what it looks like if we were building it with a if we were building it in our lab, we'd have a battery, and these resistors actually look like this. The ammeter looks somewhat like this and this. But when we draw it like this with resistors and batteries like this. So here's what we're going to do. Let's go ahead, and I want to measure the resistance across the voltage gain across this battery. And I want you to notice that I can control the resistance in the battery. Now, yesterday we said that ideal battery has no internal resistance. All right. Well, let's look at this battery. I'm going to make it ideal. I'm going to make its internal resistance 0. And so now there's no current. I'm going to say show current. Oh, let me show you one other thing. Watch. When I close the circuit, the switch, that shows these charges marching through here, which is, by the way, a little bit faster than they normally march, but that's okay. And so you can see that. Now, notice over here, I can choose conventional current. And because of a mistake of history, something that Benjamin Franklin said, or the way he notated it, he switched the positive and negative. So we have this conventional current of positive charges flowing out of the battery, out of the positive end of the battery and returning to the negative end of the battery. That's not what's happening. This is more consistent with what we have. But when we do physics, when we do electrical engineering, most of the time we talk about conventional current, positive charges going from positive to negative. Now notice that when I open the switch here, the voltage is 9 volts, and when I close the switch, the voltage is 9 volts. And there's a voltage drop across this resistor of 4.5 volts when that switch is open, and there's a voltage drop across this resistor of 4.5 volts, sorry, when the switch is closed, I mean. And so that's what we would expect, okay? But watch what happens now when I put a little bit of resistance in the battery. And I'm going to put about 2 ohms of resistance, similar to the problem that you did a few minutes ago with Kristen. Now I have 9 volts, but watch what happens. When I close my switch, I only have 8.18 volts. What happened? Well, there is an internal resistor here. You can't see it. It's not actually in there, but it functions as a resistor. And that internal resistor is causing a voltage drop, and we can see the voltage drop is exactly 9 minus 8.18, or that's going to be 0.82 volts. We have the current, and it looks like we've got, there's our 2 ohms right there. So that's where we can see the voltage drop. All right. I really want you guys to go to this site, PHET, circuit analysis, play with this, try some different things. It'll make a huge difference for you. All right, let's look at some of those AP problems over here. So this is the so-called lab questions. And so a lab question is a question where they actually give you data and they ask you to draw conclusions and comment on the lab. So it says a physics student wishes to measure the resistivity of slightly conductive paper that has a thickness of 1.0 times 10 to the negative 4 meters. The student cuts a sheet of the conductive paper into strips of width 0.02 meters and varying length, making 5 resistors labeled R1 to R5. So the student has 5 strips of paper of different lengths, not 1, but 5. And using an ohm meter, which is something that you can use to measure the resistance, the student measures the resistance of each strip, and the data are recorded below. And so here's the different resistors, and here's the different lengths. And so it says, use the grid below to plot a linear graph of the data points from which the resistivity of the paper can be determined. Include labels for both axes. Draw the straight line that best represents the data. All right, now let's take a look at this. I did not include this graph because I didn't want to do the graph. I don't want to take our valuable time drawing out the graph. I think certainly graphing is something that we certainly don't know, but we imagine that you won't be asked to graph on this year's exam. But we do imagine that you could be asked to comment on graphs or to talk about graphs or to modify a graph. So we don't know. We'll see. But let's look at this. It says we're going to plot a linear graph. Now, my question for now, what I want us to look at right now is, what would we plot? Okay, now we're looking for the resistivity. That's what the whole big, that's the enchilada. That's what we're looking for. And in every graph, we have the independent variable usually on the x-axis and the dependent variable on the y-axis, and that's usually, that's y and this is x. And so we say, well, what can we make up that will fit into this form of our best old friend y equals mx plus b, the linear graph? And so we look at this and we say, well, our relationship that we're interested in, the actual relationship is, we know there's only one formula that has resistivity that we've studied. And so that's going to be that R is equal to resistivity rho times L over A. Okay. And so we ask ourselves, what should we plot on the y-axis and what should we plot on the x-axis? Well, when we're doing a graph, we're looking to plot something on the y-axis like that. And then we say, well, what's our dependent variable? What are we changing? And you can see that what we're changing is the length, and the independent variable is the resistance. That's what is changing because I'm changing the length. So my independent variable R goes on the y-axis. My dependent variable is going to be the length. Now, I have a choice. I can either graph the length, or I could graph the length and divided by the area. Now, the way this graph is, this problem is written, it seems fairly obvious that they just want you to do the length, okay? But the reason I mention it is because there's a question later on, and this is what we think could be something that could be asked. We think this is a very conceptual way that AP likes to ask questions, so we threw it in here. And so let's assume that I'm going to go ahead and go with the first one. I'm going to go with measuring, putting the length on the x-axis, and that's going to be measured in meters over here. And over here, let me make sure it's in meters. And over here, I'm going to have the resistance, and that's measured in ohms. Always label your axes. AP gives usually 4 points for every graph that you draw. So if they ask you to do that, you would do that. And so what we're going to get is we're going to get a linear graph. But let's look at the important question. What is my slope? Okay. And so if you look at this, I'm going to rewrite this. I'm going to say R is equal to, okay, and then I'm going to write rho over A times L. And then right below this, Y is equal to mx. And look at that. So my slope is rho over A. All right, and that's how you would do this problem, is you would set that up and you would graph that. Now, look at this. After taking your data, you learn that due to a calibration error, the actual thickness of your paper is, well, let's see, hold on a second. I'm going to back up for a minute. I think I brushed over something a little bit too soon, and I want to make sure that I make the point correctly. Okay, so notice that your slope is rho over A. So you would, if you were asked to find the slope, maybe AP is not going to have you graph something this year. Maybe they'll give you a graph and say, what is the slope? I don't know. We don't know. And so you would find that, you know, that's going to be your delta R over here. And that's going to be your delta L. And then, of course, what you're going to do is you're going to say your slope is equal to rho over A. So you're going to say rho is equal to your slope times A. All right, let's go with that. Now, let's move on down to the next question. It says, after taking your data, you learn that due to a calibration error, the actual thickness of your strip of paper is 1.5 times 10 to the minus 4. So this is what you thought it was. You thought it was 1.0 times 10 to the minus 4. It's actually 1.5 times 10 to the minus 4. And if you've done enough physics labs, I'm sure that that's happened to you. Usually it's a factor of 10 that we drop or we lose, so it's not unusual. Explain how your graph would look different when you correct it with a new thickness, or explain why it looks the same. Now, hopefully what you would be able to say is, look, if you haven't graphed the area, which is what the thickness goes to. Let's kind of get some geometry here, because maybe I'm going over this too much. Imagine this is your paper. All right, now your paper, the width, all of these widths are 0.02 meters. That's 2 centimeters, 2 centimeter strips. But the thickness, that's very tiny right here. And then here's our length here. So it was hard to see the difference between 1.0 times 10 to the minus 4 and 1.5 times 10 to the minus 4. Although coming to think about it now, you would feel the difference, but maybe. All right, but anyway, it was measured wrong, calibrated wrong. And so what's different about it? Well, here's the question. When you graphed your data, did you have the A in there, the area? And the area, remember, is the thickness here, this much, times the width. That's my cross section. I'm sorry, not this distance, but there's my cross-sectional area right there. That's cross-sectional area. And so did I have it in my graph? Well, if I graphed the resistance and the length and I didn't graph the cross-sectional area, it's not in my graph. So I would say, the way I have it, that my graph is the same because the width doesn't get graphed. And then I would say maybe a little colon, it is used after I find the slope. I'm trying to convince the reader, and that's a fancy AP name for the grader. I'm trying to convince the person who's going to grade my test that I understand that that wasn't a part of the slope because I didn't put it in there. So anyway, that's what we thought about that one. Let's take a look at one more and then we'll set you loose. It's Friday night. I'm going to get places to go and things to do. All right, so we've got this other problem here. We've got a student performs an experiment to determine the EMF and the internal resistance R of a given battery. The student connects the battery in series to a variable resistance R with a voltmeter across the variable resistor as shown in the figure above, and measures the voltmeter reading V as a function of the resistance R. The data are shown in the table below. And so here's our trials, here's our resistance, voltage. And so what we're doing is we're varying that. That is our independent variable. And we are measuring this. And these are just numbers that are carried over. Okay, so they've done some math for us, but this is my independent variable and this is my dependent variable. All right, so first it says derive an expression for the measured voltage V. Express your answer in terms of R, script E, little r, and physical constants as appropriate. All right, so let's do that. All right, so I want to kind of telegraph something that we're going to be getting into next week, and that is Kirchhoff's laws. And if you remember Kirchhoff's loop rule, it says that the sum of voltage gains and drops around a closed loop has to be 0. Now let's look at this loop. We always start at the battery here and we go this way. And then we will, I'm going to do this in another color. So imagine my current is moving around the loop this way through this resistor and then back. Okay. And this is a series circuit, which means my current is the same everywhere in the circuit. Now you might want to ask me, Roger, why is there no current this way? You've hooked this up to this voltmeter. And now that's going to come up later too, but I want to tell you why. Unless you hear otherwise, we assume that all voltmeters have an infinite resistance. They are ideal voltmeters. Now, all voltmeters, no voltmeter has an infinite resistance, but most of the time it's a fine approximation. I'll talk about when it's not a little bit later. So that's our current, and it's going through there. And so they want us to put we're going to use the loop rule to go ahead and figure out what this expression that they've asked us to find. So let's go ahead. We'll say that the voltage gain is right here. Okay, that's my voltage gain, E. And then as soon as I pop out of there, I have a voltage drop across little r. It's a resistor, so I have a voltage drop. And then I have a voltage drop here across big R, and that all has to, then I come back to the battery, so that has to equal 0. Now, let's say what these things are. We learned yesterday that due to by Ohm's law, and we said the current is the same everywhere, this is going to be I little r, and this is going to be I big R, and that's going to equal 0. Now, you might ask me, well, Raj, if they asked you to find the voltage here, this V, right? This is V here. I'm going to actually even, let's kill the R because that's confusing. You want to find this V, why did you change it to this? The reason is, you'll see why, I want to get rid of that I, and it'll be easier mathematically to do that. All right, and so this is going to be I times big R plus little r is equal to 0. And so we're going to solve for V. Here's where my V comes in. Watch this. I've got this voltage and I've got this current, and I know that this current is V over R. That is known. This is known. And so E minus V over R times big R plus little r is equal to 0. I'm going to do some algebra on this. I'm going to get this to the other side, V over R positive, R plus little r. And then I'm going to solve for V. I'm going to say V is equal to the EMF times R over R plus R. And so the first part of the problem is done. They've asked me to express the derive an expression for the measured voltage in terms of R, E, and little r, and I did that. All right, so the next part is, the next thing that we are going to do is, okay, let's try that again. Okay. Great. Now, the next problem says, rewrite your expression from the previous to express 1 over V as a function of 1 over R. Okay, so let's go ahead and look at that. And so we're going to say, well, if that's true, then 1 over V is equal to R plus R over script R. All right, now, I don't yet see this, but I know I can do some math over here, so maybe it'll pop out. The 1 over R will pop out when I do this. So let's see, I could say, well, I could take it out here. I could say 1 over R times, and then what's left? We have R plus R over R, but that is not going to get me there, apparently. So I'm going to go ahead and say this is R over epsilon R, or ER, plus little r over ER. Now, when they cancel there, now I can say that 1 over V is equal to 1 over R times, over here, R over E plus 1 over E. Now, I want you to look at this. You might be scratching your head again going, well, why is that better than what I had before? Well, the reason is, here we go, R over E, is because look at what I have here. Now I have independent variable, the thing that I'm changing. I've got the dependent variable. I've got a slope, and I've got a y-intercept. And so that allows me to solve this crazy puzzle. And so now my y-intercept over here on the grid below says, plot the graph of 1 over R. Now, I've plotted it for us here, and I've labeled it for us, but they want us to find the using the straight line, obtain the values for the following. And so they want us to find E and R. Now we already said by our formulation here, let's put it back up here, 1 over V is equal to 1 over R times little r over E plus 1 over E. All right, now remember, what's the unknown here? The unknown is that internal resistance. We don't know it, but look at where it shows up. It shows up in the slope, that internal resistance. All right, I'm sorry, over here. I'm pointing to the wrong thing. That is my X, my Y. That's my X. There's my slope, and there's my Y-intercept. And so this is 1 over E, and so that's 0.08 is equal to 1 over E, which means that E is equal to 12.5 volts. And so that gives me my EMF. And then they want me to find R, and so that's going to come from the slope. So the slope M is equal to R over E, and that means that R is equal to M times E. When I find this point here, and I find this point here, and I do my slope, I find that the slope is equal to 0.052. Okay, and my EMF is 12.5, which gives me a resistance of 0.63 ohms. And then finally, we have down here, so there's my 0.63 ohms. Let me put the 12.5 volts. Using the results, calculate the maximum current. I is equal to V over R. And so we have 12.5 volts over 0.63 ohms. And that gave us 19.8 amperes, which is nothing you want to be close to. All right, now last, I want you to look at this one, because this is what, again, we're looking this year at probably a lot of explain problems. So let's look at this explain problem. A voltmeter is to be used to determine the EMF of the battery after removing the battery from the circuit. 2 voltmeters are available to make this measurement, one with low internal resistance and one with high internal resistance. Indicate which voltmeter will provide the most accurate measurement, the one with low, the one with high, or it will be equal accuracy. All right, now, this is a tricky problem. Let's imagine again, let's talk about what a voltmeter is and how it works. All right, so a voltmeter, we're going to put it on the battery, and we want to see how much voltage there is across here. Now we know there's a tiny little, let me draw it, I guess, over here. We know that there's this little invisible, unseeable resistor in there. All right, that's part of that voltmeter. That's part of, I'm so sorry, it's in, oh, we're talking about the resistor in here. So let me back up. Remember, a voltmeter, we mostly assume it has infinite resistance because we don't want any current to go through it. However, all voltmeters have some resistance. 10 have non-infinite resistance, 10 mega ohms, or something like that. So do we want our voltmeter to have a little resistance or a lot of resistance? I'm not talking about that guy right now. All right, well, if my voltmeter has a lot of resistance, that means that I will have a voltage drop across here that could become significant if it had a low resistance, because there would be a current through here. When there's a low resistance, there's going to be a good current. And if there's a good current, there'll be a voltage lost here and not showing up here. So I'll get a low reading because I'll have a voltage drop here. Now, I looked at this problem and it came over the heading of, is this a stupid problem? Because if you look in most physics textbooks, they'll talk about that all voltmeters have very large resistors. However, I called my friend who's an engineer and I asked him, and he said, well, there's a very small niche of, if you're measuring a tiny voltage on the order of, well, he didn't say, but I'm imagining a very, very small voltage, picovolts. In those cases, you want to have a small resistance, not a big resistance. Anyway, there it is. I spoke too long, but I did want to tell you that you should work these problems hard. This is a really amazing opportunity to take this test with all your notes in front of you. So if you prepare that way, you have a really, really great shot this year. So we hope we can help get you there. Kristen, any word for our wise scholars for the weekend?
No, just enjoy it. Enjoy time with family. Hopefully there's some good weather involved. And yes, on these problems, just always be thinking, what is one thing you could change in the situation and how would that change everything else? So
excellent advice. All right. Have a great weekend. Above all, be safe, and we'll see you back here next Monday, same time, same channel.